Hello guys, I am Dr. Devendra Mishra, working as Assistant Professor in Chemistry at Birla Institute of Applied Sciences, right? Also running this Tetrahedron Chemistry Classes channel, and here are the links available to approach me. Hello friends, welcome back to the Tetrahedron Chemistry Classes. So guys, in today's class I am going to discuss the synthesis and the properties of transition metal nitrosyls. Not only pure nitrosyls but also carbonyl nitrosyls, nitrosyl halides, all types of the complex which are possible for the nitrosyl ligand I'll discuss today, okay? And later on the lecture I'll discuss some aspects of the infrared spectroscopy of your complexes which contains your nitrosyl ligand. Right, if you haven't seen my previous lecture on the bonding mode of nitrosyl, then it is advisable that you must see that lecture number 9 actually, because without understanding that lecture number 9, it is little impossible to grasp the things of the current lecture. Okay, so in today's class guys, I am going to take the synthesis of the transition metal nitrosyls first. Okay, I have already written all the reactions because writing reaction while delivering lecture actually consumes lot of time, and it is also the theoretical part. That's why I am not actually writing the equations during the lecture explanation. Okay, so there are various methods important, right? So this is lecture number 10, and first method is the direct replacement by using NO. That means you will use the nitrosyl ligand, right, and you will directly replace one of the ligand present in the carbonyls, right, and then you will get your metal carbonyl nitrosyls. Okay, this is how you can do that. So your first reaction is what? Pentacarbonyl iron. When reacting with the 2 of the nitrosyls, it is actually removing 3 of the carbonyl from there and producing this particular complex. Now it is very important to understand, when your NO is present in the positive ion species, I have explained you in the last lecture. So it would be a 3 electron donor. Okay, and your carbonyl, because these two are isoelectronic species, 6 plus 8, 14 electrons are there in your carbonyl, right? And similarly 7 plus 8, that is 15, and positive charge is there. If you subtract 1 from there, then you will get the again 14. So these two species are isoelectronic, so they can be comparable and they can replace one another in the organometallic compounds. Fine. And this carbonyl is a 2 electron donor. So this is something very important which you should keep in mind while synthesizing this particular compound. So in that case, you are actually putting 2 of the NO positive you are putting here. Okay, and that means you are putting 6 electrons, 3 to 6 electron to the system. So you have to remove 6 electron from the system also. So what you will do, you will remove 3 of the CO, because one CO actually having 2 electrons, so 3 CO will have 6 electrons. Okay, so that's why this preparation is there. And one more thing which you can do by yourself, you can count the electrons of all the species, right? So electron of this species and electron of this species will remain same during the reaction. Actually it's an it's a 3D8 system, this iron is. So it's an 18 electron system. It is also an 18 electron system. You can count the electron by yourself. Okay. Now see, before going further in the reaction, I'm going to tell you a very, very important thing here. See, if you remember the preparation of my transition metal carbonyls, then in that case we use actually the excess of carbonyl to produce those complexes. But when you prepare this nitrosyl complexes, you cannot use actually the excess of the nitrosyl, because see, direct use of nitrosyls, the synthesis requires very high temperature and high pressure. In case of transition metal carbonyls, there is no problem with the high temperature and high pressure with excess of your carbonyl. But in case of the nitrosyl, if temperature and pressure is too high for the synthesis of these complexes, so this high temperature and pressure can cause unfavorable oxidation and your complex may decompose, right? So that's why it is advisable not to use the excess of this high temperature and the pressure, but you use the sources of the nitrosyls actually. So here some of the sources of nitrosyls are given. We will use all, we will discuss all of these one by one. So you can use NOCl, you know NO is positive here. You can use NOBF4 negative, and even you can use the concentrated sulfuric acid. Okay, then you can use the alkali metal nitrites like potassium nitrite, sodium nitrite, etc. And then you can also use the nitrosonium salts. So these are the some of the sources by which you can actually produce your NO for the reaction. And this is your second reaction where hexacarbonyl chromium reacts with the 4 of NO. So when it reacts with the 4 of NO, then in case you can see the hepaticity is going down. Here chromium is connected with the 6 carbonyl, so hepaticity is 6. But here chromium is connected with the 4 NO, that means the hepaticity of 4. So in the previous case you have seen the hepaticity changes from 5 to 4. Right, 2 to the 4 ligands are connected. Here in that case also you are observing that hepaticity is changing from 6 to 4. Okay, and then 4 of NO you will use to balance the reaction, and I have explained why it is happening. So you can correlate the things which I have explained actually in first reaction, and by using that hint you can count the electrons of 4NO and 6NO and then get the idea of how it is happening actually. And it is very important. You can see this tetra nitrosyl chromium. In that case you can see it's a very rare example of the pure homoleptic complex. It's a homoleptic complex, right? You know the homoleptic complexes are those complexes which are having all same kinds of the ligands. So these ligands are same, that's why it is homoleptic ligand. And see, in the transition metal nitrosyl, it is very rare that you get actually the pure nitrosyls compounds. Why you don't get the pure nitrosyl compounds, I'll come to that point also later in the lecture. But this example you can take as an special example, because in that case you can see the pure nitrosyl complexes there, right? And then you can go for this particular reaction, right, where a MnCO5I and you are reacting with the 3NO and liberating one of half of the iodine from there and 4 of the CO, and you can count the electron of I, half of I2 and 4 CO, then it would be equal to the 3NO by using the same concept which I have explained for the first reaction, and it will result in this particular complex, right? Again you can see the hepaticity is changing from 6 to 4. Okay, and then your reaction number. These 3 examples were the examples where you are having only one core metal center, but in that case you are having the 2 metal, right? That means one metal bond is there. And when you actually see, this is a dimer kind of the species, right? So when you connect this species with this, react with this 2 of the nitrosyl, right, and then you will have 2 of this complex and 2 of CO will remove. Again you can see, if you count the electrons inside and electron here and there, then you will find, okay, in this case 2NO will replace actually 2 of CO. You can apply your brain by calculating all these things. However, in examination this thing would not be asked generally, right? But you should know the concept. And then after that you can see this is very important reaction, guys, very important reaction. In that case you are actually reacting with potassium hexacyanoferrate 3, actually potassium ferricyanide. So I have written the ionic equation, potassium is not there, and when you react with this NO, then you will get this particular species, right? It will remove the cyanide negative and NO positive. Again you can count the electron present in cyanide and NO, so these 2 are equivalent. And this ion which I have produced here, it's a very important ion. If you remember, it's a nitroproside ion. Okay, so I will write nitroproside ion, very important ion. And these are the some of the representative nitrosyl complexes which are particularly important for the examination point of view. I'll explain the little things about this nitroprosides ion also, okay? But this is very important reaction for your examination point of view. And on the other hand, you can take the potassium ferrocyanide also. Here you have taken ferri because 3 negative is there. It will make the 3 positive charge over there. This is ferrocyanide. That means it is in 2 positive, iron is in 2 positive, and this is something different reaction. It is not the direct replacement by using NO, but in that case you are using this nitrite salt. See, it may be your sodium nitrite, it may be your potassium nitrite, and you are using the aqueous condition. right? When you do this reaction, then you will produce again the same ion, which is the nitroproside ion, right? In both the cases, you are producing the same thing. So these are the two important methods for the generation of the nitroproside ion, right? And cyanide will remove from here and 2 of the hydroxide, and same reaction can also be done with the nitric acid. However, it is not possible for the nitric acid, so you can stick for the 2 of this reaction. You can skip this nitric acid part from here, okay? And one more important reaction you can do, same potassium ferrocyanide, you can react with this 30% of the nitric acid. Take this compound and boil this compound with the 30% of the nitric acid and cool and separate the potassium nitrate crystals from there, and after that brown filtrate is neutralized. Whatever the brown filtrate will left actually after the removal of the crystals of the potassium nitrate, actually you will actually neutralize those this brown filtrate with the sodium carbonate, and when you do these reactions separately, then you will get your ruby red crystals of this particular nitrosyl compound, Na2FeCN5NO.2H2O. So water of crystallization is also there. So this reaction is again very important reaction. So these are the some of the reactions which are very important for examination point of view, okay? Then you can see here, guys, another reactions. Reactions of okay, fine. So there is no problem because I have discussed this nitroproside ion. So before going further in the synthesis of the transition metal nitrosyl, it is good to explain the chemistry of the nitroproside ion. It is very important, okay? So what are the reactions for this nitroproside ions, right? So as I already told you, these nitrosyl complex actually because they are the metals are generally electron deficient, okay? So any nucleophile can attack on the nitrogen of the NO positive. So the important thing is that in all the cases which I have shown here, actually your NO is generally present as the NO positive species, that means the 3 electron donor species, okay? Now you have taken your nitroproside ion and say you have your sulfide ion, right? You may take your Na2S, sodium sulfide in that case, and sulfide ion will act as the here nucleophile. So that nucleophile actually will attack on the nitrogen. So previously I said that this iron or the central metal is in the lower oxidation, having the positive charge electron deficiency, but I'm not sorry for that particular part because I am doing the reaction on the nitrosyl part. So I'm focusing the positive charge present on the nitrosyl. So it's a linear mode, right? So it will attack on this nitrogen and you will get this particular complex. It's a very important reaction, right? And this is the test of the nitroproside ion also, because this compound will have the specific color, purple color, okay? Purple color. So this is the test actually. And similarly what you can do, you can react with this particular ion, sulfite. Previously you have reacted this nitroproside ion with the sulfide. Now you will react with this sulfite ion. You can take the sodium or the potassium sulfite. Again 2 negative charges there, so it will act as the nucleophile. And again this sulfite ion actually will attack on the N terminal because it is positively charged. You know, in the linear mode the formal charge on the nitrogen is +1, okay? So it will attack here and you will get this particular species. This is again a very special test, and you will get rose red color for this one, rose red color. So these are the two reactions, reaction with sulfide and the sulfide, right, where you can identify the presence of the nitroproside by observing the purple color in the first case and rose red color in the second case. And this is the third reaction where you can use the another nucleophile, which is the hydroxide ion, and this hydroxide can also attack on the N terminal of the NO positive. So it will produce it will have this kind of the compound, right, FeCN5NO2, right? But remember, this oxygen would connected with the nitrogen, not with the oxygen, right, with the removal of the 4H2O. Okay, then you can go for the little about structure of the nitroproside ion. Basically in that case I have already told you NO positive is there, that means the linear linkage is there. So I have shown you iron, nitrogen and oxygen. Almost linear nature, right? Almost linear nature is there. And say this is your nitroproside ion. And you know, in that case, if you count the electron, so iron is in +2 oxidation. So this is the compound where the iron is in 2 oxidation state. You can very easily calculate. Cyanide is -5 and it is +1. That -5 will go there. So -5 will become the +5. +5 and 2, that will give you the 2. And then again this will shift here. So it will give you the 2. So it is in 2 oxidation state, right? And you know, when it is in 2 oxidation state, it's a T2G6 system, right? It is a T2G6 system. And you know, the cyanide is a very strong ligand, so the crystal field energy would be very high for this particular complex, and all the electrons will get paired in the T2G orbital. And when they get the paired in the T2G orbital, this means the species is the diamagnetic in nature. This is very important. Okay, so I have written here, you can see this is your iron, this is nitrogen, this is oxygen. These are the lone pairs present on the oxygen, though I haven't shown the lone pair over there, but you can consider the 2 lone pairs here, one lone pair here and 1 lone pair here. And this is the nitrogen, and this is the pi anti-bonding orbital of the NO positive, right? So how to get this pi anti-bonding molecular orbital of the NO positive? If you remember one of my last lecture, right, in that case you can see now, when your NO is acting as the NO positive in the linear mode, so first it will donate this particular electron to the metal, then these two would be vacant, and when these two vacant, and after that the metal will donate electron to these anti-bonding molecular orbitals, right? This is important. So that's why I have shown here, this is the pi anti-bonding molecular orbital of nitrogen which are vacant, and these are actually the T2G orbital of the metal which are filled. 6 electrons are there, and they will actually donate the electron to this molecular orbital, right? So it will result in the pi bond, right? And Fe and nitrogen, it is actually nitrogen will donate the electron pair here, so it is a sigma bond, right? So sigma and pi, it's a double bond, it is having the double bond character, and it is almost linear actually, right? So it's a diamagnetic species because I told you all the electrons will get paired since cyanide is the strong ligand, okay? And since it is a linear species, and I told you that in case of the nitrosyls, exact 180-degree angle is not expected for the linear complexes. It is having the range of 165 degree to 180 degree, as I have told you in my last lecture actually. So here it is found that the bond angle is 178 degrees, right? And this nitrogen oxygen bond length, right, this is somewhere around 113 picometer, right? 113 picometer. And then what is expected then? Bond length, generally you see, if you have free, I have written here, if you have the free NO, then it is having the 115 picometer, but in that case you can see the bond length is slightly lower, so obviously it will also affect the their stretching frequency in the IR spectrum. For free NO, the IR stretching frequency is somewhere around 1800 at 76. Actually it is having the range, but in that case it is found that it is 1876 centimeter inverse, since bond length is just like that. And now in that case the bond length is smaller, then obviously it would be a little stronger bond and higher stretching frequency will require. So in case of your linear in this particular complex, it would have the 900, and it is found that it is having the 1940 centimeter inverse of the IR frequency. Okay, however I will also explain the IR spectroscopy in little detail later on the lecture. So this is all about your nitroproside ion, which is very important for your examination point of view. And then another reaction, use of the nitrite or the nitrous acid. However, I have explained this reaction already here. You can see here I have explained this particular reaction, use of the sodium nitrite or any nitrite in the aqueous solution. But see, I am taking 1 or 2 more example for this one. Now this is the carbonylate ion. See, earlier I was preparing by using the neutral carbonyls. So these all are the neutral carbonyls or the cyanides, okay? But here I am taking the carbonylate ion. So I have explained the carbonylate chemistry in detail in one of my lecture. If you haven't seen that lecture, you can go through. Okay, by typing the transition metal carbonylate complex by tetrahedron chemistry classes, you type in the YouTube and you will get the results in the search bar, and then you can go through the lecture. So this is my cobalt carbonylate ion, right? Because negative charge is there, that's why it is carbonylate. When react with the nitrous acid in the acidic condition, right? So it will produce this particular complex, and removal of the CO and H2O would there. So these are the theoretical part, right? So you can learn some of the reactions. Okay, there is no need to learn the byproducts, but you know, you must know about the species, right? And obviously, since in that case you are producing this particular complex, right? So now if you can do the reaction in another way also, what you can do the nitrite right, or the nitrous acid or the nitrite conditions, and carbon dioxide atmosphere environment of carbon dioxide you will take, and in the aqueous medium, so this will produce the carbonic acid, you know. So it is the carbonate ion, bicarbonate ion, sorry, and it is carbonyl, and you are producing the same complex which we have produced earlier. Okay, and then another very important method, use of the nitrosonium salts. Okay, so nitrosonium salts, you know, this NO would be positive, this would be negative, and this is again positive, this is negative, this is positive, and this is negative. So either of these salts you can use. Now this reaction is another very important reaction, very important, because in that case I am taking this VASKA'S complex as the starting material. So trans triphenyl phosphines and trans carbonyl and the chloride. Okay, and you are taking this NO4 negative. So in that case you can see the VASKA'S complex, you know, it's a square planar complex. VASKA'S complex is square planar. Coordination number 4 is there, and when you react actually this VASKA'S, because it is coordinatively unsaturated, that means it is having the vacant species. So this NO positive will get attached here actually. So I was not having the space over there, that's why I have put it in the downside. You can put in the top side also, both will not make any difference. So it's a positively charged species because you are adding the NO positive, right? And of course it is present in the salt form, and BF4 negative would be there. And this is actually square pyramidal complex. Coordination number is 5. So this geometry is actually square pyramidal. Square pyramidal. Okay, and of course hepaticity is also changing for the iridium. Here it was 4, here it is going to change to 5 actually, right? And similarly with the help of these examples, you can take this rhodium complex with NO positive to produce this particular compound. Okay, again the theoretical part. Then you can cyclopentadienyl anion, and you can take this rhenium complex. Okay, and then you can react with this NO. The same reaction would happen actually, but in that case one of the CO will remove. Right, so you can ask, sometimes you are removing CO, sometimes not. In that case we cannot remove CO because we are not having this CO here. So you are having the C and R. R could be anything, your ethyl, methyl and anything. Okay, then you are getting this particular compound. And then you have some special kind of the carbonyl compound where you have the linkage between the two different metals, tin and the tungsten. Right, you are having two metals, and these are connected with two different kinds of the ligands, right? And negative is there, and you can react with this NO positive, you know, it will actually knock out one of the CO from here. Okay, and then you are having NO attached to that tungsten, right? So this NO will get attached to the tungsten. So it is better if I write actually if I wrote the bond in just that manner, NO, right? But however it will not make any difference. You can understand these are the little things. And use of NOCl, you know, in case of the NOCl it is NOCl and NO positive and the Cl negative. What you can do, you can take this tetrakis triphenyl phosphine nickel, and you can react with the NO positive and Cl negative. Two of the triphenyl phosphine will remove from here, and you will get this particular complex. Okay, so it's a strong sigma donor. Recall, it's a strong sigma donor. Okay, and then you can take another carbonylate ion, and you can react with this NO positive and Cl negative, and you will have this particular complex, right? Cl negative and CO will be knocked out, and you will have this particular compound. Okay, And finally, the last reaction, use of the ammonium hydroxide in the basic conditions. And this is very, very important because this is the method which produces actually your cyanido-nitrosyl complex. That means whatever the complex would result, they will have the cyanide as well as the nitrosyl. So you are taking your tetracyanonylicate 2 ion in that case, and ammonium hydroxide you can take, and you can take any alkaline solution. You can take sodium hydroxide, you can take the potassium hydroxide, where M represents the alkali metal. Sodium, potassium metals are generally important. Okay, so this is something very, very important. Okay, and then you can see this particular compound where cyanide and nitrosyls are present together will produce this compound. Rest of the side products are there. And in the last reaction, you can take the hexacyanochromate 3 ion, will react in the same conditions, right? And you will get this particular complex. Okay, so these are the some of the important properties which are very, very important for examination, entrance examination point of view, as well as for the MSc students, because this literature is little difficult to find in the textbook if you don't have the better facility. See, we all are not studying in the IITs or NITs or in the reputed university. So we are actually studying sometimes in the colleges which who don't have much of the facilities. So for those students, this literature is particularly important. Okay, so this is something very, very important. Now I am going to discuss some of the very, very important representative compounds, one of two, right? And first is the ROUSSIN'S salts. So ROUSSIN'S salts are of two types, red salts and the black salts. And this is very, very important question for your NET GATE examination, right? And as well as for your MSc examination. Okay, so what are the ROUSSIN'S salts? Basically, they are nitrosyl thio compounds. When thio is there, that means the sulfur is there. Okay, and basically they are the complexes of the iron 2. So representatively what you can write, M2Fe2NO4S2. This is how you can write. So however it is better if I write the reaction in this way, the exact writing of the formula. These metal ions are present outside of the coordination sphere. Okay, so this is important. So this is your red salt, ROUSSIN'S red salt. That's why I have used the red pen for this one. 2 of the irons are there, Fe linkages are there, right? And they are connected with the 4 of the nitrosyls. 2 2s are 4 if you check here, and 2 of the Sr group is there. S is the sulfur, R you may take the ethyl or the methyl or some other group. Okay, so I am putting the Sr and Sr, so they are forming the bridge. This is something very, very important, and it is found that this particular iron bond length in your ROUSSIN'S red salt is 272 picometer, and the bond angle between these two irons which are connected with the sulfur is found to be 74 degrees centigrade. 74 degrees. I am very sorry. And your positively charged ion could be anything. It could be your sodium series, like you may have your sodium, potassium, rubidium, cesium, anything, but lithium is not there. Okay, or you may have the ammonium ion also. So either of the alkali metal series or the ammonium ion, you can take any salt, right? So it is having this kind of the structure. This is something very, very important, ROUSSIN'S salts. Okay, and why I am discussing these ROUSSIN'S salts, because see, they are having, see, if you recall some of the chemistry in the biological systems, so this NO is very, very important. This nitrosyl is very, very important because you know this actually nitrosyl, what it will do, it is actually the muscle relaxant. Okay, and when it is the muscle relaxant, that means it will use in the biological system. And these ROUSSIN'S salts are also having the very good antibacterial properties. So they are the molecules of importance also, medicinal importance also. Okay, and this is the red salt, and the structure is comparatively easy. And you can see here, this is the black salt. The structure of this black salt is a little difficult. So I have drawn this structure for you, but I'm also going to explain how you can draw. What you can do, you can actually put all the iron in the tetrahedron. So 1, 2, 3, 4. So you can make a tetrahedron for this iron, for these 4 irons. Okay, and what you can do with all the irons, then you can connect with the linear NO linkage. All are linear in nature. Remember, all NO are linear in nature. Okay, except this one. So, sorry, not all actually. This is you guess all are actually the linear. So in that case, you can see the linear, 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 linear. All are linear in there. So how many was there? NO 4 NO was there. 1, 2, 3, right, and 4, right. With the center, it is also having the 4. Okay, and then you can 1, 2, 3, 4, 5, 6, 7. Okay, 7 are there. So you can connect all the Fe. See, first Fe with the NOs, then second Fe with the NO, then third Fe with the NO, right, and then fourth Fe with the NO, and then you will satisfy the coordination number for the iron. So connect all of them with this one. Now you left with the sulfur. So after preparing this, put all the sulfurs here and connect this iron with the sulfur, connect this iron with the sulfur, and one of the sulfur would present in the center of the tetrahedron, and this sulfur you will connect with this iron, with this iron, and with this iron, and with this iron. So however, it is not very important to mug out this structure, but you may have some idea about the structures also, because in your entrance examination question may be there. You may have the 4 different kinds of the complexes, structures of the complexes, and you have to identify the black salt, black ROUSSIN'S salts. So if you want to find the black ROUSSIN'S salts, that you can easily predict, okay, this is the complicated structure, this goes to the black salt. However, this red salt was having the simple structure. Okay, and again you can see this is the negatively charged species, and over there you may have the sodium, potassium, rubidium, cesium, any ion can be present here. Okay, and the important thing about this structure is that which may be asked in the examination. So the question is just like that. You can see the Fe and 2 Fe are in the base, so there would be a bond length between the Fe and Fe. Then 1 Fe here and 1 Fe in the apex. Obviously there would be the bond length between the Fe, and you can see this bond length actually is, seems to be higher in the structure already. So it is very important when iron base and iron base, they are connected. So when they are in the base, so they are having the 360 picometer of the bond length, nearly 360 picometer of the bond length, and this bond length would be slightly shorter, 270 picometer. So this is something very, very important. Okay, and one more important thing you should note, this actually black salt is more stable, and why it is more stable, you can get that idea because it is having, see, chelate formation, right? It is forming a ring compound. In the coordination chemistry, you know, the chelate compounds are more stable, so it is forming a chelate, so that's why it is more stable, while this red salt is less stable, right? In fact, what you can do, if you leave that red salt in the air, it will gradually convert to the black salt, and when you treat that black salt with the ammonium hydroxide, then again it will get back to the red salt, right? So this is something very, very important. It is so unstable. If you actually leave, if you stand this compound in the air or in the solution, right, not air but in the solution, so it will get converted into the black salt, and when you treat that black salt with the ammonium hydroxide, it will get back to the red salt. So this is the little thing which you should know about this thing, right? And the important thing is that in that case, you can see the iron is in +2 oxidation state, right? And in both the cases, they are found to be diamagnetic in nature. Their magnetic behavior is what? Diamagnetic in nature. Okay, this is something important. Okay, now this is the most important part, very, very important part, and listen carefully, because whatever I will explain, I am not able to write the entire thing on the paper, but you should understand. Stability criteria: pure nitrosyls versus nitrosyl carbonyls, nitrosyl halides, nitrosyl cyanides, and nitrosyl thio compounds. So here in the first of my preparation, I already told you this is the only, it is a very, not only, but it is the very rare example where you are having the 4 of the NO. It is very difficult to find the pure nitrosyl complexes because they are not very, very stable. Remember, these pure nitrosyl complexes are not very, very stable, right? So how we can explain this thing? For example, you can take what I can do. say I am having Fe and this 4 NO are attached here in that case. Okay, so you know the how the stability, carbonyl compound stability for the carbonyl compounds, double bond character produced between the metal and the carbon. See, if you take the carbonyl complexes, Cu complexes, okay, so in that case, if your metal carbonyl bond gets the double bond character by back bonding of the other ligands which are connected, right? Then the stability actually would be there. Similarly, if you are talking about the stability of the nitrogen, then there should be metal nitrogen double bond and they have the double bond character. When they have the double bond character, their stability increases. First of all, you should understand this particular point, and after that I am coming to the very important point. Now, say for example, all the NO which are connected to the Fe are NO positive, that means or are linear. And you know that in the linear mode, they are the 3 electron donor, right? So what will happen when actually when you actually add one of the if you recall my previous lecture, you know, when you react with this NO positive in the linear mode with the iron, that means the metal's oxidation would be reduced by the 1 unit, right? It is very important. I have explained in the last lecture. And what will happen if all the NO, if all the 4 NO positive, that means in the linear modes, are attached here? So what it will do, it will actually increase the electron density on this metal because they are the 3 electron donor. So metal will get unnecessary negative charge over there. This is something very, very important. I am repeating, listen carefully, right? If all the NO positive ligands are in the linear mode, that means this metal, due to this 3 electron donor property, will get the negative charge. And you know, the putting the too much of the negative charge on the metal, it's not a very, very favorable situation for the complex. Okay, so that means all the compound would not be linear, all the NO would not be linear in any complex. Okay, and similarly, I can take another example. Say you are taking NO negative now. So it is, you know, NO negative is what? It is bent, and in the bent form it is 1 electron donor. So when it is only the 1 electron donor, that means the electron density would not be there on the metal and it will get the excess of the positive charge, because in the mechanism I told you, in that case the oxidation number increased by the 1 unit. When NO negative is attached in the bent mode, it will increase the oxidation state, and when it is attached in the linear mode, it will decrease the oxidation state by 1 unit. So in that case, in NO negative, this metal will have the excessive positive charge, right? When it is having the excessive positive charge, it is also not a very good situation. So all the nitrosyls which are attached with this particular complex cannot be linear, cannot be cannot be bent. In fact, your this complex is having 3 of the linear combination and 1 of the bent, that means NO negative. So all 4 NO are not same. You may have this question in your examination, whether all the NO group attached to this Fe are same or not. Then your obvious reply would be no, 3 are linear and 1 is bent actually. So now this is something very, very important. Now again, what you can do, say you are taking these complexes. Now they are the nitrosyl carbonyls. Now identify the nature of the carbonyl, whether it is pi acceptor or it is a sigma donor, right? I told you the pi acceptor or the sigma donor nature of the ligands in one of my earlier lecture of the coordination chemistry. Okay, and similarly you can see here I is there. You can identify it as sigma donor or your pi acceptor, right? And similarly VASKA'S complex are there if halides are there. And cyanides, you know, cyanide is what? You know, it is again you can identify whether cyanide is sigma donor or pi acceptor. You know that this is cyanide is the pi acceptor. Okay, and similarly your nitrosyl thiocomplexes, rosin salts. So why I have written all these classes? Because it is not possible to get the purely nitrosyl compounds due to the stability criteria, because both the situations will actually not stabilize the complex. However, in some cases it is found that they adjusted themselves by adapting the linear combination of N by NO on and bent nature of the NO connected with the metal actually. But see, if you have I have already told you, if you have actually the sigma donor, right, say for example you can take this I as the sigma donor. So what it will, this sigma donor, it will do, it will actually give the electron density to the metal. Okay, and when it will give the electron density to the metal, then it will form back bonding with this one, so it will stabilize the complex. If it is the pi acceptor, so if extra negative charge is there, so this pi acceptor ligand will actually take the electron from this complex, right? Again it will stabilize the complex. So both, whether the sigma donor or whether the pi acceptor, both can stabilize the complex. I have explained these things in my last lecture, if you recall. You can see this cyanide is the pi acidic or the pi acceptor. I already told you. Okay, and I have also explained these things. Okay, and then you know, this is sigma donor actually in case of, so sigma donor will also stabilize this one. So generally in the bent mode, if you have the bent mode, NO negative is there, then you require the sigma donor. Sorry, it is not in the frame, very sorry. Say if you have the bent mode, then you will need the sigma donor, because bent mode, in the bent mode it will have the positive charge, metal will have the positive charge, so sigma donor will actually donate the electron density to neutralize this charge and give stability to the complex. But if you have, right, in that case it is the linear mode linkage. When it is having the linear mode linkage, that means it is having the excess negative charge. Okay, so to neutralize the negative charge, you should have the pi acidic ligand, because this negative charge will be donated to the anti-bonding molecular orbital of this pi acidic ligands. Okay, this is very, very important. So this actually I was explaining here. That's why I told you, if you haven't seen my previous lecture, then it is a little difficult to understand the things. I hope this is clear why the pure nitrosyls are rare and why we have the nitrosyl carbonyls, halides, cyanides and the thiocomplexes, because pi acidic as well as the sigma donor. So if it is the sigma donor, right, that means it is in the linear mode. Okay, now because you know in the linear mode it will increase the negative, sorry, it is in the bent mode, very sorry. If it is in the bent mode, then you will require the sigma donor, and when it is in the linear mode, you will require the pi acceptor, right? This is very important. So I have I can write here, bent NO will have sigma donors to stabilize the complex. Linear NO will have pi acceptor to stabilize the complex, right? If you want to understand the things in the detail, then you can go for this Asim K. Das, Fundamentals of Inorganic Chemistry by Asim K. Das, and it is there in the volume 6. The explanation which I am giving you, it is given in the volume 6, and you can find a review of the research paper also on your transition metal nitrosyls actually. There also they discuss the things in the detail. I hope this is clear to you. There is no problem, right? And after that you can see what you can do. I can check some of the important ion if they are present here. No, they are not present here. So one important thing I would like to discuss, this compound, brown ring test of nitrate. Brown ring test of nitrate. See, you have learned this test in your class 12th actually. So in that case, the brown ring which is formed, it is having FeNO and 5 of water would be there, and 2 positive. Now suppose this question is given to you in your examination and you have to identify whether this NO is linear or bent. So you focus here on H2O. H2O is what? It is sigma donor. Water is sigma donor. And you know when sigma donor ligands are there, the NO must be in the bent form. So in this case, NO is in an bent form. Okay, so this is a little application of this bounding test. So you can identify the nature of the NO by analyzing the nature of the other ligand. Okay, I hope this is clear to you. And after that, okay, I haven't written anything over there. So now I am going to complete this compound, this lecture with a little idea about the IR spectroscopy. IR spectroscopy of transition metal nitrosyls. Important, right? This part is very, very important for your examination point of view. Very important. So first of all, you should remember some of the data which is necessary. So I'm writing here, if you are having the free NO, point number 1, if you are having the free NO, then it will have the nitrosyl stretching frequency which appear on the IR spectrum somewhere around 1876 centimeter inverse. So this reference I am giving you, and if you are studying some other book, then you may find some other value of instead of 1876 you may find 1900, you may find some other value. It depends on the literature which you are referring. Okay, because these values are generally not absolute, right? So in that case, it is having this value. Now say you are having free NO positive. Now you expect, now what is your expectation? The nitrosyl frequency would be higher with this 1876 or lower with this 1876. So I am telling you, see how we can prepare this NO positive. If you remove one of the electron from the anti-bonding interaction, then it will give you the NO positive, right? That means you are removing electron from the anti-bonding molecular orbital. So bonding interaction would become higher. When anti-bonding electrons gone, then bonding interaction would be higher. That means the bond length would be smaller. And bond length would be smaller, then it will require higher energy to stretch, which reflect in the higher value of the stretching frequency. Higher value of the stretching frequency. Wave number would be higher if you remove the electron from the anti-bonding molecular orbital. So NO positive we are producing by removing an electron from the anti-bonding molecular orbital. So anti-bonding interactions becomes less, bonding interactions would become higher. When bonding interaction would become higher, bond length goes down, and when bond length goes down, so it will require higher energy to stretch the bond, and higher energy actually reflects in the higher values of the stretching frequencies. So for NO positive, this value should be higher, and obviously it is NO. It is found somewhere around 2300 centimeter inverse. You can refer the molecular orbital diagram again and again to understand this. Say I am giving you the situation number 3. This was the point number 2. I am giving you the point number 3 here. Okay. So what is the point number 3? Now you are having metal bound NO positive. Metal bound NO positive. Now what do you expect? You know NO positive is what? It is 3 electron donor and it is now metal bound, right? So what you expect in that case? The value should be higher or the lower than the 300. See, NO positive is not having any electron over there. But when it is metal bound, so metal will donate electron into the anti-bonding molecular orbital. That means the anti-bonding interactions increases. When anti-bonding interactions increases, that means the bond length would be larger, and for larger bond length, less energy required to stretch the bond, and this less energy will reflect in the lower value of the stretching frequency. So definitely when this metal bound NO positive is there, it must have the stretching frequency which must be lower than the 300 centimeter inverse, because You have donated electron to the anti-bonding molecular orbital. Again, you can refer that diagram again and again to understand these things. So what would be the exact value? It will depend upon the type of the other complexes, right, like sigma donor or the pi acceptor. So we can write only the it would be less than 2300, but exact value will depend upon the type of the complex actually, and these things you have to learn actually. Okay, and if they ask the question in the examination, they will give you the value, or they ask the suggested trend, then you have to apply your concepts actually. So right, and then you can go for the point number 4. See, very important, if you have the nitrocell complexes, right? So generally these nitrosyl complexes have the range for the linear stretching frequency, and this range somewhere around 1660 to 1900 centimeter inverse. Linear linkage means metal connected with the nitrogen connected with the oxygen, linear linkage. Okay, and if you have say new NO negative, so again it will have the range. So what range for NO negative would you expect? It should be lower, that is 1500 to 1600 centimeter inverse. I already told you in case of the bend form, right? See, this is the bend form. In the bend form, that means, say, why it is actually going lower for this one. See, free, you know, it is somewhere around 1876. For linear it is 1600, and for bend it is again going down actually, right? This is important to understand. Some of the things you should note actually. And so how you can write? NO positive stretching frequency would be higher, free, 2300 centimeter inverse, followed by nu of NO, free, okay, it is also free, and the value is 1876 centimeter inverse. And after that you are having nu NO negative, and it is found that it is having the range of again it is free, and it is having range of 1500 to 1600 centimeter inverse. So this range you should know actually. Okay, and you can understand all these things by actually considering the molecular orbital diagram. See, it is higher, it is lower. So why it is higher, why it is lower, it can be very easily explained with the help of the molecular orbital diagram. Okay, this is something very important which you should know. And after that, the last thing which say number 5, bridged nitrosyl complexes. Bridge nitrosyl complexes. So you know the bridging of NO could be of any kind, mu3, and it could be of mu of NO, mu2. Okay, these linkage I have already explained. And then you are having terminal of NO, not bridged but terminal. And in case if you have followed my lectures on IR spectroscopy for carbonyl compound, then you know when bridging increases, then carbonyl stretching frequency goes down, and the same is true for this one. So if your nitrosyl is bridged between the 3 metals, then this will have the very lower value, 1300 to 1340 centimeter inverse. Okay, and when the 2 bridges are there, that means the value would be lesser than this, greater than this one, not lesser. So it would be somewhere around 1480 to 1540 centimeter inverse, and for free it is 1672 centimeter inverse. That means the lowest for mu3 and highest for the terminal. Why?